Hello students, in this video we will study refraction of light. As you can see in the figure here, there is a cup and a spoon is inserted in it. It appears to be broken. This is due to refraction of light. Let us study it in detail. Here you can see that a beam of light is traveling in one transparent medium, and after striking at the interface, it is falling on the another transparent medium. You can see that the light is striking at the interface at some angle. That is, the direction of propagation is here oblique of the incident ray. It enters the another medium and changes its direction at the interface. The angle which the incident ray is making with the normal, let it be represented by I, that is angle of incidence. Now the refracted ray is making an angle with the normal, let that angle be represented by R. As you can see in the figure, the direction of the incident ray changes at the interface. Now this change in direction is termed as refraction of light, or in the simple language you can say it is simply the bending of light. So when a ray of light passes obliquely from one medium to another medium. Here we have considered one of the medium as air and the another medium can be water, glass or any transparent medium. Then the change in the direction of the propagation of light can be seen. This bending of light at the boundary when it passes from one medium to another medium is termed as refraction, as I have just told you. So, the basic cause of refraction is the change in the speed of light as it enters from one medium to another medium. So, we can say that the incident ray changes its direction or bends in the another medium because the speed of light in that medium is different from the earlier medium. So, due to this change in the speed of light, the incident ray appears to be bent either towards the normal or away from the normal. When the ray is passing from rarer to denser medium, that means when the ray is passing from one medium to another medium in which the first medium is optically rarer medium into another medium which is optically denser medium, then that ray will bend towards the normal. That means when we are traveling from rarer to denser medium, the ray will be bending towards the normal. And if the ray is traveling from denser to rarer medium, then the ray will bend away from the normal. So you can see here in the figure that one medium here we have considered as air and the another medium is water or even glass. Air is an optically rarer medium as compared to water. So the ray of light is entering from rarer medium towards the denser medium. Hence it will bend towards the normal as is shown in the figure. So from here we have understood that the basic cause of refraction is the change in the velocity of light from one medium to another medium. Now let us understand the laws of refraction. See here, this is the incident ray. Whenever the ray of light strikes from one medium to another medium, a part of it gets reflected back in the same medium. See here, a part of it gets reflected back in the same medium, and the rest of the light enters in the another medium, which we call it as refracted ray. So, let the angle of incidence again be represented by I and angle of refraction be represented by R, as we have just seen in our previous slide. So, the laws of refraction, the first law is the incident ray, the refracted ray and the normal to the interface at the point of incidence all lie in the same plane. See, incident ray, normal and refracted ray at the interface. This is the interface where the ray, incident ray is striking the other medium. They all are lying in the same plane. Now see the second law. For a given pair of media and for light of a given wavelength, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant. That means sine of angle I upon sine of angle R is a constant value. Now this constant value is termed as refractive index. See, let us suppose that the refractive index of the other medium be represented by mu2 and a refractive index of the first medium, if it is an air only, then also its refractive index is represented by mu1. Then the ratio of sine I upon sine R will be a constant, and that will be equal to the refractive index of other medium divided by refractive index of the first medium. You can even write it like this, that it is mu2 upon mu1, or it can be represented in this manner. So this is a constant value called as refractive index of the medium. You have to remember this formula in order to solve the numericals. So the question comes, what is refractive index? Refractive index is actually the characteristic property of the medium, and its value depends only on the nature of the material of the medium and the color or wavelength of the light. So we can define the refractive index as the ratio of speed of light in vacuum or air to the speed of light in the medium. Let us see here. So we can define absolute refractive index of a medium, which is the ratio of the speed of light in vacuum to the speed of light in a medium, like this. Or you can say the absolute refractive index of the medium is speed of light in medium 1 upon speed of light in medium 2. Again, you have to remember this formula. So we can say that a medium with higher refractive index is optically denser medium as compared to the medium which is having lower refractive index. Like we have written here, refractive index of optically rarer medium is lower than that of the denser medium. That means if it is a rarer medium, it will have lower refractive index, and if it is a denser medium, it will have greater refractive index as compared to the other medium. In refraction, the velocity and wavelength of the light changes. This is the cause of the refraction, but frequency and phase of the light do not change at all. We have seen in the previous slide also that the velocity is the root cause, basic cause of refraction of light. So we can say velocity and wavelength are changing, but frequency and phase will not change at all in refraction. Now let us study refraction of light through a rectangular glass slab. For this, consider this figure. Here, this is the incident ray which is striking the interface of the two medium, where one medium is the rarer medium and the another one is the optically denser medium. Let the rarer medium is represented by A, that is, it is having refractive index of mu A, and the denser medium is having refractive index of mu B. So the incident light is striking at the interface. Let the interface be represented by L. At this interface, the incident ray is making an angle I1 with the normal. As the ray is traveling from rarer to denser medium, it will bend towards the normal like this. Now let this bent ray is striking the other parallel side of the glass slab. At this point, let us name it as M. And now it is moving from denser to rarer medium, so it will travel away from the normal as shown. Let the angle of refraction here is R2 and the angle of incidence with which the bent ray is striking the parallel side with the normal is I2. Let delta be the angle of deviation which first ray after refraction is making. That is, the angle of deviation is represented by delta after first refraction. So the refraction at first interface can be written as sin I1 upon sin R1 is equal to mu B upon mu A. And the refraction at the second interface at M can be represented as sin I2 upon sin R2 is equal to mu A upon mu B. So we can rewrite them as mu B upon mu A, and here we can write down as mu A upon mu B. So when we multiply both these equations above, we will get as equal to 1. See here, this is mu B upon mu A and this is mu A upon mu B. So when we will multiply both, we will get as 1. So definitely when we will multiply the sine terms also, then also we should get 1 like this. Now see in the figure, this is a normal and this is also a normal. That means both the lines are parallel to each other. If both the lines are parallel to each other, this R1 should be equal to I2 because these are alternate angles. That means these are alternate angles, alternate interior angles. If these two are equal, that means here in the above expression, sin I2 upon sin R1, these two, as they are equal, they will lead to 1. So we are left with these two terms now, and on the right hand side we are having 1. So definitely these two terms should also cancel each other. That means I1 should be equal to R2 because this will only happen when this term and this term are equal to each other, and this will only happen when I1 is equal to R2. So from here we can conclude that the angle of incidence at the first interface should be equal to the angle of emergence by which the light is leaving the glass slab. So now we can find the lateral displacement of the ray on passing through the parallel slab. That is this. For this, let us draw a perpendicular on the original incident ray direction. Let it be represented by y. And let this be represented as n. Consider this triangle. That is triangle LMN. Triangle LMN. In this triangle, we can find sine delta. As this is perpendicular, the sine delta will be equal to Mn upon Lm. See clearly in the figure, this is perpendicular and this is the hypotenuse in the figure. So we can rewrite it as y upon Lm. Now see in this triangle, that is in triangle L, let this be L dash. In triangle L, L dash and M, let us find cos R1. It will be base LL dash upon hypotenuse, that is LM in the figure. LL dash can be written as T, that is the width of the parallel slab, upon hypotenuse, that is LM. Now, in order to find this lateral shift y, I will put Lm from here in above expression like this. Y will be equal to sine delta into Lm, and Lm we have just calculated as T upon cos R1. So we can write down the lateral shift as T into sine delta upon cos R1, or we can even write down in terms of the known parameters, that is delta can be replaced in terms of I1 and R1. See, this is the normal and this is the incident ray. The same incident ray is redrawn with the same direction like this in the denser medium. So we can say that I1 is equal to R1 plus delta, because they are now vertically opposite angles. So from here we can calculate delta is equal to I1 minus R1. So the same we have replaced the delta here. So we have obtained this expression for lateral displacement. Y is equal to T times sine I1 minus R1 upon cos R1. So from this expression of lateral displacement, we are very much clear that this lateral displacement is proportional to thickness T of the glass slab, and it will increase with the increasing angle of incidence. So in this video we have understood what is refraction of light, then we have studied various laws of refraction, and then the refraction of light through a rectangular glass slab. Thanks for watching. Please like, share and subscribe.